Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have AAS Journal author Takehiro Yoshioka with us today. And my apologies for my Japanese. How are you?
Yeah, fine. I am Takehiro Yoshioka, a graduate student at the University of Tokyo.
Very cool. How far along are you in your graduate career? Are you first year, second year, almost ready to graduate?
Second year PhD student.
Okay, very cool.
No, first year.
I look forward to calling you Dr. Yoshioka. That'll become soon. So is spring happening in Japan yet? Do you have little flowers, or is the trees blossoming?
Yeah, I saw the cherry blossoms last month.
Oh, very cool.
Already, the flowers disappeared, unfortunately, but that was beautiful.
Yeah, makes it a little warmer. A little warmer. Very cool. Good. Takehiro, what do you like to do for research?
Yeah, I'm interested in high redshift universe and early universe. So I'm now working on the reionization.
Okay. Of the early universe. Very good.
Yeah.
And that will bring us to this very lovely APJ article. It's open access, people. You can go get it. Chorus 4, mapping the spatially inhomogeneous cosmic reionization with Subaru HSC, and Takehiro, take us away.
Yeah. This article is about inhomogeneous reionization in the high redshift universe.
You have a lot of co-authors.
Yeah, co-authors from the University of Tokyo and Waseda University and so on, and National NAOJ.
Yes. Good. So why don't you say a little something about reionization?
Yeah, reionization is a transition, phase transition in the universe that in the early universe, the universe was filled with neutral hydrogen, but after the formation of fast galaxies and stars, the strong radiation from the fast objects reionize the neutral hydrogen. This is called
Reionization.
Cosmic reionization.
Very good. Good. Yes.
Cosmic reionization is happens sometime in the high redshift universe that is completed by around redshift 6 or 5 points, blah blah blah.
Yeah.
The process of cosmic reionization is highly dependent on the distribution of ionizing sources, but the ionizing sources are still under debate. So then the cosmic reionization is thought to be processed spatially inhomogeneously because ionizing sources existed in distinctly. Studying in the process of reionization is important for collecting the details of formation of fast stars and galaxies and black holes.
There we go. Good. Good.
In the recent 20 or some years, the reionization is studied by Lyme alpha emission lines.
Yes.
And the Lyme alpha fraction is one of the widely used methods for the reionization. In recent studies in the literatures, Lyme alpha fraction, recent studies reported Lyme alpha fraction is going up between redshift 4 and 5, but on the other hand, redshift above 6, Lyme alpha fraction sharply drops.
Right. Yes.
Redshift above 6. This is regarded as a signature of reionization in that redshift.
Yes.
But in such studies, measuring the Lyme alpha fraction is measuring Lyme alpha fraction requires spectroscopic observation to measure the Lyme alpha flux. So in such studies, the survey areas and the number of objects, number of samples are very limited. So such previous studies is limited to the average neutral fraction in that redshift. Yes. So to overcome this difficulty, we use Subaru hyperspring CAM data, which has very large field of view.
Yes.
The HSC field of view enables us to efficiently detect high redshift galaxies, so we can map the reionization in the large field of view. So
very cool.
So we can investigate inhomogeneous reionization in the largest area so far.
There you go. Perfect. Very good.
Yeah. In this paper, we observe the Lyme alpha emitters LAEs and Lyme umbrella galaxies LVGS at redshift 6.6.
Okay.
Then we calculate the Lyme alpha fraction, which is defined as a fraction of Lyme umbrella galaxies that show Lyme alpha emitters, Lyme alpha emission line.
Okay.
Yep.
Cool.
This paper is structured as 6 sections. First one is introduction. In section 2, we describe the observational data, and in section 3, we explain the object selection, such as LAEs and LVGs. In section 4, we calculate the distribution of LAEs and LVGs, and draw the Lime alpha fraction map.
Yes.
This is the important important result in this figure, in this article.
Cool. Yes.
In section 5, we describe the reionization simulation to calculate the neutral fraction. Then we summarize this paper in section 6.
Okay.
Yeah.
So we have some filters.
Yeah. Figure 1 shows the transmission curves of the filters we use in this article. The important one is yeah.
Yep.
Blue one and red one.
Oh yeah.
Blue one is NB921, which detects the Lime alpha emission line at ratio 6.6.
Okay.
Then the IB945 is a brand new filter we installed on HSC to promote this research. This is important for selecting Lyman-Blake galaxies at redshift 6.6. This is described in section 3.
When we get there. Cool. Good.
Yeah. Okay, let's move on to section 2.
Yes.
Yeah, we use HSC data in Cosmos field. It is about 1.5 square degrees. This is the most largest area in the measurement of Lyman alpha fraction.
Yes. That's the biggest survey today. And sort of a blow up of the effective area. So what causes the white regions?
Yeah, white regions, the mask region for removing the areas which is affected by bright foreground stars.
Foreground. Okay. Great. Okay. A few holes. Yeah. Swiss cheese a little bit. Very good. Okay. So we have a pipeline. Going to define our color functions. And then alpha selections. You want to talk a little bit about the selections?
Yeah. Section 3, we describe the object selection. In section 3.1, we explain the LA selection. Yes. LA selection is basically similar to previous studies. NB921 is efficient for selecting the LAEs at ratio 6.6.
Yeah.
And we use Z minus NB broad flux excess in narrowband.
Okay. Yes, I'm with you. Oh, it's okay. Got it. Okay.
Yeah.
I'm with you. Good. Okay.
Yes.
All right. And there's some of our data analysis. And then we got the LVG selections.
Yeah.
Okay.
LVG selection, we use Lyman-Blake technique, which is basically mostly used in high redshift universe. We select the blue UV continuum and sharp break between Lyman alpha or Lyman limit. To detect the Lyman-Blake, we use Y band and Z band and Y band and IB945. This is this selection criteria is shown in figure 5.
Let's see what we got. Figure 3, figure 5. Really, figure 5. That's your color.
Figure 5.
Okay.
Yeah. This red line shows our section of Lyman break axis at ratio 6.6.
Okay.
By using the IB filter, the x-axis shows the IB minus y. Using the IB minus y criteria, we limit the Lyman break axis up to ratio 6.8. By using the IB filter, we can narrow the ratio range of Lyman break selection compared to the typical Z-drop selection.
And blue and green. So what is the blue and the green?
Blue is
okay, so the greens are dwarf
green
stars.
Points
are
dwarf stars in the Milky Way galaxy.
Got it.
Which is contaminated, which can contaminate the LVGS at high ratio universe, high ratio galaxies. Then the blue one is blue one is also stars in
green and blue are stars of various forms. Okay.
To distinguish stars and galaxies, we show the blue and green points in this figure.
Very good. Looks like you have a nice color magnitude diagram here.
Yeah, now figure 4. Figure 4 shows LA selection. Z minus NB shows flux excess in narrowband. We can
relative to this one. Okay. Yes.
Yeah, as a function of narrowband magnitude.
Okay.
Yeah. Then the blue points as LA candidates we selecting this study.
Yeah. Good. Okay, so these are cuts. CMD, anything above 6.5. Okay, good. I'm with you.
Yeah, thank you.
Good. And
let me explain the section 3.3, which describes the completeness measurement. Yeah, as usual, we estimate the section detection and selection completeness by using the Monte Carlo simulation. This simulation, we mock the high ratio galaxies. We create the mock galaxies and embed in the observed image, and we process the mock images with mock galaxies, and in the same way as observed images. And so we calculate the completeness by calculate the rate of recovered galaxies in the among the embedded mock galaxies.
Yep, I'm with you. Good.
By using this simulation, we can estimate the redshift distribution of the observed LAEs and LVGs.
Okay.
This is showing, the result is showing figure 9. Yeah, thank you.
Okay.
Figure 9 shows the redshift distribution of LAE, LVG, and normal typical Z0 galaxies. Blue one is the redshift distribution of LAEs, our LAE candidates, and this is very narrow, around redshift 6.6, between 6.5 and 6.6. So to calculate the LA fraction in this redshift, we have to select LVGs at almost the same redshift. But the typical Z-dropper galaxies spans 6.5 and 7.5. They're very narrow. So by using the typical Z-dropper section, the LVG is very contaminated by foreground or background LVGs compared to LAE at 6.6, redshift 6.6.
Fair enough.
So to narrow the redshift range, as we explained in section 2, we use IV945. By using the IV945, the
dropout
redshift range of our LVG candidates narrow, as shown in this orange line curves.
Yes. With you.
Yeah, some say in this plot still have very there is a difference between LAE and LVG redshift distribution. We consider this slight difference in the reionization simulation to correct the difference and calculate the neutral fraction.
Yeah. Okay.
Okay, section 3 is okay, I think.
Okay.
Then I'll move on to section 4.
Section 4, results, surface density. Yeah. Okay.
Yeah, thank you. Section 4, we calculate the surface density of LAEs and LVGs. The result is showing
Figure 10.
figure 10 and 11.
Yes, let's start with figure 10. These are the...
Yes, sorry to move forward and backward again and again.
It's all good. It's all good. So I read a paper anyway.
Section 10, figure 10 is LVG surface density, and this shows the result is consistent in the previous studies at redshift 6 and 7. So our selection is reasonable.
Good. So that's the it's LVGs, and then we got the LAEs.
Yeah, figure 11 shows LAE surface density, and this is again consistent with previous studies. So we conclude that our LA section is worked fine.
Representative. Good. Okay.
Yeah.
So that's completeness.
In section 4.2.
Spatial distribution.
Yes.
Good idea.
We calculate the spatial distribution of the objects using the Gaussian kernel density estimation. Now, in this method, each object has some Gaussian kernel density distribution, and superposition of each objects we can calculate the spatial distribution by superpose the distribution of each from each galaxies. Then the result is shown in again figure 13.
13. Let's go to figure 13. Ooh, nice. Very good. Let's start on the left.
Left one is the LAs and right one is LVGs.
Oh, okay.
The black point is the observed LA candidates, and the background colors shows the distribution of objects. Number is calculated, and the number shows over density delta, which is defined as density excess compared to the average averaged number density. So the over density 0 shows it where the density is same as the cosmic mean, and going the higher delta, which shows the over density of LAs or LVGs in this figure. As shown in this figure, the LAs and LVGs exist differently.
Yes. Yep.
In LAs, LAs are very crowded in the south of this field of view, but LVGs also have over density at north in the field of view. This is, I think, the interesting result in this study.
Good. And somehow seems like divide these two, and figure 14 seems like the important part, the most important part.
Yeah. Figure 14.
Most important
we
part.
Calculate the map of number ratio of LA and LVG.
Yes. Those two maps.
This figure, we calculate this figure by dividing the LA distribution divided by LVG distribution, as shown in figure 13, and The background green color shows
the
number density
distributions.
ratio between LAE and LVG.
Yep.
And the blue points and red points shows distribution of LAEs and LVGs respectively. This figure we can find that LAEs and LVGs exist differently in spatially.
Yes. Yes.
And
cool. Very good.
So as shown in introduction, LA fraction is the indicator of reionization or neutral fraction in the universe. So by using the relation, we think that high LA density region in this figure, that is the east part of this figure and west part of this figure. Such high LA density region, we think that reionization is in progress, but on the other hand, low LA density region, such as very bright area in this plot, that in such regions reionization is delayed. So say such area might have neutral hydrogens.
Got it. Yeah, because you do have to have that.
Much neutral hydrogens.
Right. Right. Okay. Very nice result.
Yeah. This is about section 4. Next, in section 5,
yes, we did.
We use reionization simulation to calculate the neutral fraction. To calculate the neutral fraction from the result of Lyman-alpha fraction in the figure 14. So we use a result of reionization simulation. But that simulation is high resolution radiative hydrodynamical simulations, and combination of n-body simulation to calculate the density evolution from the density evolution of the dark matter halo. Then from the result of n-body simulation, this simulation calculates the distribution of stars and galaxies, and from the outputs of from such early galaxies and stars, we calculate the radiative transfer in the IGM to calculate the reionization. Then
okay.
Yeah, this strong point of this simulation is that the LAE, this simulation calculates the LAE, yes, Lyman-alpha emissions are very precisely simulated in this simulation. So we can compare the result of the observation and the simulation of LA fraction.
Okay.
Then next, we calculate XH1. We calculate the relation between XH1 neutral fraction and LA fraction.
Okay. Simulations.
Yeah, in the simulation, we select the LAEs and LVGS in the same way as the observation, and by using the result of reionization simulation, we calculate the neutral fraction at that redshift.
Right.
By comparing the result of LA distribution, LA and LVG distribution, and neutral fraction, we derive the relation between the neutral fraction and Lyman fraction. The result is shown in figure 15.
Figure 15. You. All right. Here we go.
Yeah.
Oop, missed one. Oh, my bad. Okay, figure 15. There we go. This one. Right. Number fraction.
Yeah. Thank you.
Yes.
This shows the relation between XH1 and LA fraction. As expected, the neutral fraction going higher, the LA fraction goes down because line of emission is attenuated by the neutral fraction and neutral hydrogen. Then by using this relation, we estimate the neutral fraction from the result of LA fraction.
Good. Cool.
The green horizontal lines shows averaged LA fraction in our observation. So although the uncertainty is large, but we can conclude that the average neutral fraction in the field of view is estimated by the XH1 is lower than 4.4 as an 1 sigma upper limit.
Okay. 4 there. Okay.
Yep.
Good. Yeah, 1 sigma.
So
nice.
Using the same method, theoretically, we can estimate in principle, we can estimate the neutral fraction, this distribution of neutral fraction compared during the figure 14 and 15. We have the distribution of Lyman fraction and the relation between XH1 neutral LA fraction, but as shown in this as shown in figure 15, the uncertainty is very large. So unfortunately, we cannot quantitatively derive the neutral inhomogeneous distribution of neutral fraction. But in this figure 14, we we estimate that the reionization is we think that the figure 14 shows that reionization is proceeded spatially inhomogeneously.
Okay. Yeah, you already yeah. Okay, good. Yeah. All right.
I think this is the most important part of this figure in this article. But
good.
Next part, we estimate how deep observation is required to quantitatively derive the XH1 inhomogeneous XH1 distribution.
Okay. Yep. Put that together. Yep. Yeah.
And also in the simulation, we calculate we discussed how we distinguish the XH1 distribution and large scale structure. Say we observed the LA fraction distribution of LA fraction in figure 14, but LA fraction distribution is also dependent, is of course dependent on the neutral fraction, but on the other hand, LA and LVG fraction distribution is also dependent on the intrinsic distribution of galaxies. Say that is called a large scale structure. So in principle, we have to distinguish the XH1 distribution and the large scale structure.
Yeah. Okay.
So in the simulation, we how we distinguish between the two? Yes.
Okay. Seems like that comes to figure 17, yeah?
Yeah. Figure 17 shows the XH1 map and LA fraction distribution in the simulation. In this plot shows some similarity between XH1 distribution and LA fraction. So we can we can infer that the LA fraction is dependent on the XH1.
Right.
But to distinguish, but the LA fraction is also dependent on large scale structure to distinguish the effects from XH1 fraction and LA fraction. We calculate the LA fraction between considering IgM absorption and without considering IgM absorption in the simulation.
Okay.
If the XH1 distribution also affect the LA fraction,
well, yeah, okay.
If such case, the LA fraction is differently observed by us because IgM absorption, that is the that is XH1
Yes.
fraction. So this result, this is shown in figure 19.
Right. Without.
This shows the result of LA fraction between with IgM absorption and without IgM absorption. But in this figure, we cannot find a clear difference between the two. So we cannot, unfortunately, we cannot distinguish the two in our observation data.
Right. Okay. That's fair enough.
But by using the result of simulation, we assume the very deep deep observation. We can assume the deep observation in the simulation by assuming the 1 or 2 magnitude deep observation. We might be able to detect the difference between the with IgM absorption and without IgM absorption. So we hope in next 5 or 10 years, observation, deep high redshift observation can quantitatively investigate X-region distribution in the epoch of reionization.
Okay. Good. Are you good? Do you want to cover more?
Yep.
Limits, equivalent widths.
Could you move on to figure 21?
Figure 21, equivalent widths.
Yeah. This is the last part of this article. We calculate the line for equivalent width distribution. The blue one and orange one is the EW distribution of LAs in the high area density region and low area density region, shown in figure 14. The high area density region shows high EW. High area density region is expected to be low neutral fraction. So this figure shows that low XH1 neutral fraction. Low neutral fraction means that the line of emission is easy to transmit the IgM, and AW is expected to be high. This result is consistent with that scenario.
Yes.
That's all for this article.
Good. All right. Very nice. Very nice. Takehiro, thank you so much for walking us through your very lovely Course 4 article.
Yeah, thank you for inviting me here and share our article.
Good.
Yeah, I'm glad to explain our result.
Yeah, it's a very nice result. So you mentioned it a little bit toward the end there about where we go, let's say over the next 2 to 5 years. So are there additional, well, first of all, can Subaru go deeper than what you have, or do you need more time to go deeper? Are there other multi-wavelength capabilities that could help with this? Is there additional theoretical calculations that could go with this? So just expand a little bit on this is chorus 4. Is there going to be a chorus 5? Is there a chorus 6? So just sort of where does that go over the next couple of years? Is there going to be a chorus 5? Is there a chorus 5? Will there this paper was chorus 4? Is there going to be a chorus 5?
Actually, I don't. I'm
Okay.
not sure about the future of this.
All good. All good. Okay. You mentioned it. We'll take it off. We need to go deeper to split those LAEs and LVG curves. So very good. Thank you once again for walking us through your very lovely article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.